Thank you, Ryan. So welcome everyone. So this is my 7th Notes and my first Notes AI. So really excited to be here. And as Ryan said, I'm stepping in for someone who couldn't make it. So this is a very short notice presentation. So please apologize if anything is not perfect. This is a presentation that I actually gave a few times last year before context graphs came along and so on. So I did a tiny bit of updates, but mostly it's about context engineering in general. I'm Michael Hunger. I'm VP of Product Innovation and AI at Neo4j, so working on the product side, have been here for a long time as such, and I do everything around graphs, LLMs, MCP, and agents, and so on. I want to talk about a little bit, why do we care about context engineering? What are sources of context? How does it relate to agents? And how can we use graphs for creating better context as well? Why is context engineering such an important thing right now, right? So we started out with prompting, but now lots of people are talking about context engineering, harness engineering, agentic engineering, and so on. But why is this important, right? So basically, prompt engineering was something like you did a one-shot request to an LLM, and then basically you got some answer back, right? But nowadays, actually, it's much more about basically preparing the stage for complex tasks, right? So when we are there, we want to take all the relevant information that we need to provide to the LLM or the agent to do the right reasoning, take the right steps, to actually have a very narrow view of the world as such. Like Andre Karpathy says here, it's kind of an art and science that kind of put exactly the right things into the context, which is a repeating pattern that you'll see today for the next step as such. So why does it matter now? So of course, as always in engineering and data engineering, if you put garbage into a system, you get also garbage out, right? So that also means kind of the quality of information that we put in and give to an LLM, which you already have experienced yourself, is determining also what you get out. There's more interesting work happening on dynamic prompts. How can we basically create prompts that are adapting based on what's currently available, the user information tools available, and so on. If you look at something like chain of thought, that's almost like the LLM doing a little bit context engineering to itself, because each LLM is basically what it does. It completes text, and it completes text based on what is already there. And of course, in an LLM at the beginning, there's a system prompt and the user question. But then as you build up a conversation, all this conversation also becomes part of this context that the LLM tries to complete. So you can almost use the context as a steering mechanism. Where does the model collapses its answers and where does it focus its attention? Is basically something that you steer through the context. So if you can look at this from this perspective, then something like chain of thought is almost like the LLM steering itself into the right direction of its whole kind of training weights as such, right? And these days, especially since December, of course, we work a lot more with coding agents, and we also know that, for instance, things like spectral development, agent engineering, or harness engineering are becoming more and more important, where we basically focus a lot on basically working with the agent to get the right pieces of information of a task, all the right tools at a point, and then execute the task in coding as such, right? And the nice thing about context engineering is also that it happens at inference time, at test time, not at training time. So it's much faster, much cheaper. You can flip around, change things at a moment's notice, basically. So you don't have to retrain a model or do things like that. It's something where you're super flexible in terms of what do I want to put there. From that perspective, it comes basically from the few shot examples and prompts as such, right? Something that's really interesting is also, even if you have a million token context windows, bigger context doesn't mean better context, right? We have the needle in the haystack, and I'll talk a little bit about some of the issues that are arising with larger contexts. And I think this information architecture for humans, the better you structure the information that you put into the context, the better the results are as well that you get. So as I mentioned, prompt engineering was kind of, you sent one question, one thing to the LLM. Sometimes you added a few examples, other things, tried clever phrasing, remember my grandma is dying things and so on, to get the LLM to answer you. Now with reasoning models, this has mostly gone away because they have been trained on reinforcement learning. So they are actually much more task oriented as such and completing tasks as such. So you don't have to bribe them anymore. But now it's basically we have more context available, so we can put more information there. It's more dynamic. We want to focus on goals. What's kind of the task or the step at hand that we want to do? We want to curate what we put in there. Is it relevant? Is it not relevant? Can we actually modify context so that irrelevant things are kept out of them or are compressed or condensed as well, right? So can we put in structured output inputs, things like, can we put in structured formats like JSON or YAML or other ways where we can basically give the information not just a wall of text, but can we have headers, subsections, annotations, things like that, and focus on really having more signal and noise in the context. So that's why for me, it's kind of almost like thinking like information architecture for humans. And this kind of thinking like for humans is also a recurring theme that I'll have in this presentation. Lance Martin from LangChain had an interesting point. He said basically context engineering is building dynamic systems that give the right information and tools in the right format so that the LLM can accomplish the next task at hand, right? So that's basically how can we slice and dice the information so that it exactly has all the information. It's like for the human, right? If you give someone a generic task and miss out some of the information that they need, then they can't fulfill the task. If you overwhelm them with too much information, they also can't fulfill the task. It's someone like if you have an assistant or a colleague that you want to achieve a certain task, you try to give them exactly the right amount of information to do this. And the same is what we do with LLMs as well. So what are sources of context, right? So where does context come from? So of course, traditionally, context came from prompts. So humans basically created text templates from that perspective that achieved certain tasks. Other information came from retrieval augmented generation. Basically, you retrieved information from data systems where you, of course, also adhere to things like permissions, access control, other things. That's also where GraphRag comes from, where you want to go beyond something that vector search just returns text document. You want to return and traverse structured information in your database and make this available in a structured way to the LLM. There's the conversational state and the history. You can look at things like, what has been discussed before. You don't want to repeat yourself every time that you talk to the LLM because it's already in the conversation, right? And then what happens then with the conversation state as it grows, if it reaches context boundaries and so on. So then this is where memory comes into play. Can we basically store pieces of the information of the conversation as memory that is then later available to the LLM, either actively so that the model can actually retrieve this with tools as memory as needed, or something where in some systems you also inject memory at the right points into the system. So you basically look at the task at hand, you look at the memory system and see what is relevant from the memory system and what's the right information to pull from the memory system to give to the agent. And then basically structured output from tools. As you know, agents have the ability to do tool calls. So whatever APIs, databases, other systems can provide structured outputs go also into the context. So there's a lot of sources for context. I've just broken here also a little bit in what's coming from a human, kind of the question task, the prompt, dynamic prompts. But then there's also cognitive sources of context, like for instance, if there's meta information, there's guardrails from the system, right? Things that the model should not do, protections from prompt injection, things like that, policies. Chain of thought is also kind of the self-reflective cognitive thing where the model brings in its own context, basically. Judging of results. So for instance, if there were two calls, the model judges the results. Are they useful? Are they not useful? Do I have to call other tools? Can I use this? Do I need to drill down further? These are kind of more cognitive sources. And then, as I mentioned, the memory, short-term memory, which is kind of just the conversation, what is currently at hand, but then also long-term memory where we can look at either textual, like more episodic, what kind of conversations did we have in the past, what did we talk about, but also structured ones where we actually extract entities from the memory and then use this kind of world model that's building up, which was also discussed in the opening panel as well. Can we do this? And then procedural memory, which is more kind of taking the agent interactions and storing them as part of the reasoning memory, but then also can I derive new procedures from that, right? So like we do with, with recipes, with patterns and other things, with guidelines and so on, can we actually use memory to extract new learnings that then can, for instance, be applied to new agents, right? So imagine you bring a new agent online, it can already access playbooks or other things that were derived from information that other agents collected as such. And then, of course, all the tools, data, MCP, so all the APIs, and where you can get information from other systems, of course, while adhering to security and policy concerns, which includes RAG and graph RAG as well. Some of the challenges I already mentioned, large context is not kind of the solution, right? So many people said, oh, RAG is dead because we have large context. We can just put 1 million tokens into the context. First of all, most data sources in the enterprise have more than 1 million tokens of content. And then you also don't want to drown the model in too much crap, basically, right? So you have basically these long contexts lead to context, right? So if you accumulate more and more, you see it in coding agents with ralphing, for instance, where you basically try to resort the context after each task so it has a clean set of tasks and information, but then all the other craft that has been accumulated goes away and you don't diffuse the model, right? So there's a lot of confusion that comes which also happens if you overload it with tools. So which is really interesting, right? So while a few tools are useful, the more tools you provide, the model doesn't know which tool to use. It tries to use the wrong tools. So things like tool filtering and push down or tool grouping or tool dependencies is something that's really interesting there. Clashing contexts, especially if you have contradicting information. Also in multi-agent system, what happens if multiple sub-agents return with data that's actually contradicting to each other? How does the supervisor model resolve these kind of things as well? And then large contexts also lead to distraction. So there's a lot of things in this area as well. So one idea I had was kind of something like a minimal viable context. So what's the minimum amount of information that we can put into context to have efficient usage, correct task completion, and basically efficient processing in terms of latency and so on. So what do we have? We have basically the system prompt, instructions. We have the role of the model, constraints and information. Examples from an example store, for instance, so we don't want to blow up the context with putting all the examples all the time into the context as well. Then what is the minimal set of tools that I need for this task? So can I basically pre-filter the amount of tools that I have available? I've seen agent system with hundreds or thousands of tools. If you can filter it down to what is actually relevant right now, that's important. And then of course the user requests. So and then we exclude all the filler stuff that's not relevant, right? So we want to have a high signal to noise ratio in the context as such. So if you go back to information theory, cognitive psychology, and so on, you have basically what can we hold in our short-term memory, right? What is the kind of size of our working memory? And if we can, as humans, we can do the 7 plus minus 2, right? But what's interesting is if you create structure, then suddenly we can also keep 7 of the higher level structure and 7 of the higher level structure as well. So basically, by adding structure to it, we get much more total story or total accessibility, because you can suddenly navigate the information. It's not just a wall of text, basically, but it's something that you can navigate and go deeper into as well. So that's, again, similar things as apply for humans in terms of information theory and information architecture apply here as well. I already mentioned memory as such. So we have short-term memory, the current context, the long-term memory, which is both structural when we extract entities and relationships, procedural and episodic, and we have the reasoning memory and the traces from the agent executions. And then the question is kind of what is actually relevant of this memory, how much is needed at a given time, and how can we fill the gaps in memory, right? So because not everything is perfect, and then the agent needs to decide, oh, actually my memory is incomplete here. I need to actually go back and ask the user, call some tools, and so on. And what's interesting as well is how do we basically compress, distill memory as well. So there's some things that I will talk about later. Context structure, the information hierarchy, information structures, if you can do headers, tags, kind of YAML, JSON structures, which give us substructures that the LLM can navigate. That's something that's really useful. If you have a local LLM that has file access or a remote LLM with database access, they actually can proactively use these kind of tools to fetch exactly the right information that they need, so that you don't have to put it up front in. And then, so similar to agent skills, where you have in the front matter just an overview, and then the LLM can basically use the information from the front matter to dive deeper and get more information out of it. So you kind of build up an information hierarchy as such. Try to remove the application. Usually it's better to refer back to something that is available somewhere else, and then the LLM can, or data model can go there and fetch this information from the other place as such. And this also applies to tool output. So if you can, try to deduplicate tool outputs, right? So don't try to return, for instance, from a database just 1 million rows. If it's actually just 5 rows of data and this was just an expansion or join, and because of the join you have basically lots of duplicates, then try to aggregate this into sub collections and have only like 3 lists with 10 elements each or something like that, right? And instead of 1,000 rows basically. So if you can aggregate and group things, then this is definitely preferred as such, right? But sometimes it can be helpful to, at the end, have a summarization of the information so that the LLM is reminded of, oh, what's actually there, and can refer back to that as such. So what are different approaches for offloading and dealing with large contexts? So one is kind of something that coding agents do a lot, or local agents do a lot. They use file system, Obsidian, wikis and other things to offload information. You can edit files, you can add things to files. You can have plan documents, task documents, and break it down. You can use vector database for episodic memory. You can use graph databases or other structured databases like relation databases for more structural memories. But if you have highly connected information, you would, of course, use a graph there. So you can offload it. And what's interesting, if the agent can read and write, so if it's more active in its context management, then you can also automatically consolidate things. So you can compress memory. You can use a small LLM to summarize information from the context. You can also say, I actually create a summary, but still store the full information still in a file, and then only provide a small summary to the LLM. And if it wants to dive deeper, the original information is still there. So you don't compress and throw away, but you compress, store on disk, but have then only the small summary or the key information available, so it can use this almost like a database as such, right? At boundaries, especially if you have multi-agent system, you need to prune as well, because you can easily imagine if you have like a research system with 10 sub-agents, each of them produces a lot of context, you immediately load off your context, overload your context. So each sub-agent also needs to basically already condense and summarize before it hands it back to the main agent, and kind of determine what are the main findings from, for instance, from my research. And if you can, something that's also really interesting, if you have existing memories and you know that these are not complete, are there async mechanisms that can enrich existing memories? So basically, where you can say, hey, identify gaps, and in the background something goes off, fetches this additional information, and enriches the memory as you come in. And then for retrieval of memory, you can, of course, retrieve information from third-party systems. You can go to Wikipedia, you can go to other data systems, Diffbot and others, where you basically have always the information available. You don't have to store everything that's available there. So for instance, in Cloud Code, they also said, we will not build up a local vector search. We have all the code available. We can always use grab and find to find the information. And the code is always the source of truth as well, right? So because as soon as you build up caches and downstream stores, you always need to keep them in sync. So basically, having the source of truth with good tools for retrieval there can be much better from that perspective, right? And when you have information that comes from different places, you want to consolidate it in memory, so that then you build up basically a representation that puts things into place, right? And I've seen yesterday or the day before, there was something talking about even a memory palace for agents, right? So you remember this spatial representation of information as well. And something you could also imagine this as almost like context pyramid that has like a foundational piece, which is like system prompts and the core facts, and then dynamic elements and the ephemeral outputs are stacked on top of it. So that's also a mental model how you can imagine this to be structured as such. Okay. What's also really interesting, that information is not static, right? So oftentimes we see a book and the information in that book is static, but in the information age, actually none of the information is static. Everything changes all the time, gets adapted, gets changed. We need to, of course, track and trace how information changes, because if something changed under our feet, we need to notice it and also look at things like provenance and lineage of information. But what's actually interesting here is kind of self-modifying systems, right? So because if the information itself, the context is kind of the programming language of an agent, then by changing the context, the agent can also change itself, right? So, and you've probably seen it in a few places where you have an agent, either with OpenClaw or others, where you actually have the context that the agent uses is something that the agent can modify itself. Then you can get to a self-modifying systems, which is yet another level of interesting behaviors, like you get to emergent behaviors and other things like that. So that's something I think where we are still at the beginning of understanding what's happening there, but that's a very powerful way as well. Needs to have some guardrails, I guess, because otherwise it can go off also quickly. For agents, so originally we started with chatbots that had like one-shot retrieval, basically, where RAG was more a push principle, and now with context engineering is more a pull principle. So one interesting other point from LangChain was oftentimes when the agent is not doing the right thing, it's actually not a model problem, because modern foundation models are actually really good, but that the context is not right, right? So it's basically like you give someone a task to do X, Y, Z, and you give them information that's either outdated or wrong, and then you complain about that it didn't do that task correctly, right? So, and basically it's similar to that, right? The capability is there, but if the information is not there, then you can't execute on that. If you look at the agent loop, there's actually multiple places where context plays a role. So in the reasoning phase, where you basically get access to memory, to guidance, to metadata, to plan and act and break down information. In the action phase, where you use tools to either take action, retrieve information, and get insights. And then in the observation phase, where you basically look at these results from the planning and from the tool retrieval, and then you judge, okay, do I have everything that I can that I need to complete the task or generate the answer, or do I need to do another loop in the agent loop? And if not, can I also basically use in the observation phase the learnings and compress this into memory, compress this into context that is kind of persisted for the next loop as well. So this is actually really interesting to see that in all the three phases of the agent loop, context and kind of external memory and storage is really, really important as well. Kind of breaks this down again into the multiple phases here. So there are things like, the LLM can extract parameters from the conversation to do tool calls. There are things like, accessing memory during a reasoning and planning phase. So you can see, have I done this task before? If I have done this task before, what procedural information is available? How can I make use of that, and so on? And then in the observation phase is kind of how do I compress and update and distill memory as well. So there's more to that. This is also something that I really liked from Jason Lu from Instructor. He did a really nice context engineering series. And he said basically, context engineering is a tool that helps the agent to navigate a complex information space, which I think is really nice because it has this kind of concept of the context is basically your map or your travel guide, basically, that helps you to navigate the real world. And what you put in a travel guide is basically guiding the agent to the next step. And then in the next city, perhaps they have a different travel guide and so on. So from that perspective, this navigating a complex information space resonates, at least with me, really well. If you look at tools have a really important aspect in context, both in terms of like, how do I make tools available to the agent? They basically provide agency. So because in RAG, it was we pushed information into the context. In tool calling, we have the LLM and the agent be able to pull information as needed as such. But then, of course, how do I make tools available? How do I do tool design? Like, I think many of the good API design principles apply for tools as well, like naming descriptions. There's dependencies between tools. Are they explicit? Are they implicit? I already mentioned tool outputs, structured tool outputs. How much do you output from the tools? How relevant is the tool output? Is there a lot of noise in there? And then do they also come with explainability? So the whys and the hows, is this something that you can actually provide from your tools? So that's some things to think about here as well. And for multi-agent systems, it gets one level more complex. Just looking at the clock, I'll continue to my graph section. So graphs are actually really interesting, right? So I've been in graphs for 16 years now, actually much longer, 18 or so. And graphs are really good for highly connected information. And if I look at context, especially under the view of information theory and structuring information, graphs are actually able for me to connect the dots, right? So both on the memory side, on the building a world model, capturing reasoning traces. I did a lot of graph analytics of software, and many of the things that we've done back then already are now coming back as well. And as I said, I put this presentation together last year before context graphs became a thing, but many of the aspects are also relevant here. So from a graph perspective, LLMs bring all the language skills and the reasoning and the creativity skills, and the graph provides, the knowledge graph provides the context and the enrichment and the knowledge, so the facts basically as such, and together they can do really great things as such. I won't go too much into GraphRag, just really high level is GraphRag is a way of retrieval augmented generation that uses graph data structures as part of the retrieval process. So you don't just use a vector store to retrieve the information, but you use structured information to retrieve the information as such. In a graph structure, which gives you more explainability, so you know where this information comes from, you don't have a black box, you can navigate complex patterns and go through the graph until you have all the information collected that you need to answer. And you basically also can have more control about relevancy, because you have things like confidence score on relationships, you have weights, you can basically determine, is an entity relevant for me? If yes, then I continue in this neighborhood of this entity. If the entity is not relevant, I can stop there or even skip it as well. And so I can basically almost navigate my way across this map of information in a graph as such. But also graphs capture context, right? So you've heard probably the context graph discussion at the beginning. And this is actually really relevant because graphs don't just hold data, they can also easily hold metadata, right? So it's basically graphs all the way down. And so from that perspective, they can both, on top of the data, they can capture metadata, and beneath the data, they can also capture execution and execution traces as well. So you can also capture basically how did an agent operate, what tools were called, things like reasoning memory. And so basically you can bring all these three worlds together. My colleague Will had a few really good blog posts, like one came out yesterday on this. How does this come together? Basically the metadata, the data, and then the reasoning information about agent execution. So that's really interesting because you want to basically take the reasoning information and then again condense and distill it. And you can use things like graph algorithms, for instance, on top of reasoning traces to distill, for instance, what were successful patterns, what were like frequent patterns, what were things that had shorter paths to success versus longer paths to success, or lower costs versus higher costs. So if you think about it, it's almost like a traffic routing problem in a way, right? So how do I get to my goal on the shortest or most efficient way? And then can I memorize this for the next time I get a similar task? Because then I can save a lot of tokens by not going 3 loops in the agent loop, but only one such. And so if you heard about context graphs at the beginning, so that's what Jaya said basically is it's a knowledge graph that's designed to capture decision traces. That's what I just talked about. And what's interesting is there's decision traces from humans, which are oftentimes not available because they're like tacit implicit knowledge that we don't materialize somewhere. But interestingly, from agents, we can actually look at what decisions did they make, what did they do in reasoning, how did they make choices about tool calls and so on. And we can use this information to augment the human decisions as well. If you want to try out context graphs, there's this really cool create context graph application and system that my colleague Will wrote. I really encourage you to try it out. It has lots of different domains where you can try this. And from us, from a Neo4j product perspective, we are building on top of the graph database foundation using our tools. And then we basically put an agentic layer on top of that that has like agents, agent memory, and agent integrations in the ecosystem as well. So if you want to build agents anywhere, we try to integrate graphs everywhere, both on the memory side, but also on the retrieval, tool call, and data representation side. So things like semantic layers and so on. So if you want to learn more, feel free to hit us up on these kind of things. And to close, basically, communication with an agent is not is a conversation. It's not a rigid do this. You need to express your intent, and you don't want to micromanage, but you want to give it as much control as you can to make its own choices, but you also want to give it a framing to work inside. So these are kind of the things that we've learned. Basically, we need context engineering for the specific task at hand. We can look at minimal viable context experiments as some mental models for things. Graphs are really great for context because they have connected information and rich semantic information on nodes and relationships. And they can do all the 3 layers, metadata, data, and reasoning traces. And there's lots of best practices. Speaking of best practices, in Graph Academy, we have a lot of courses on context graphs, on agent memory, on GraphRec, and other things like that. And I already mentioned the Create Context Graph dev as well. And I also added all the resources. I'll share the slides later after conference. And with that, thanks a lot and have a great rest of the conference. Thank you.